Boa tarde. Desde começou em inglês, é mais fácil continuar em inglês. Tudo bom? Perfect. Very good. So, do you have any questions from last time? Did you think of anything else? Pode fazer perguntas em português. Did you think of any? Do you have any questions since last time? No. Okay. Good. So, I will just quickly summarize what we did last time. If you don't understand anything, like the English part, you can stop. So, last time we first talked about why we should study gauge theories and gravity together, right? What were the reasons? All the open problems today: dark matter, baryon asymmetry, quantum gravity. What else? all big problems, dark energy. All these things require knowledge of both gravity and gauge theories. So, if you don't know one of them, there are chances that you may not find the answer for these big problems. But you can always write papers. You know there are two different things, right? So there are two different things. And also, not just knowing the theories, it's also good to know what are the latest experimental results, right? So what are the latest experimental results and new mathematical techniques. And also, if you have a theory, like how do you quickly make some calculation to connect with the experiment so that you know whether it's right or wrong, so that you don't spend your lifetime fooling yourself, right? So Feynman once said, the easiest person you can fool is yourself. So you can think, oh, what you're doing is correct. Yes. So that's the first part. So why we should study gravity and gauge theories together is because the open problems today require knowledge from both. That's the thing, right? Second thing, why should we study scattering amplitudes? Simple reason is the only way to check your theories, especially gauge theories, is through experiments and the experimental results. So what are the experimental observables? Observables are cross-section. Or you can say differential cross-section, so decay rates, this kind of things. These are the observable quantities. So in order to verify your theory, you will have to calculate cross-section, differential cross-section, and decay rates. Decay rate is when something decays into something else, right? This is, you can say this is same as, we say cross-section when there are two incoming and any number of outgoing. We say decay, so this is usually cross-section, so something like A plus B equals to C plus D. That's a cross-section, or it can be anything more. So usually decay means something goes into, or it can be more. Just a terminology. So these are the things. And how do we get this? By the way, so the equation for the cross-section would look like, this is the symbol for the cross-section, sigma. Would look like integral of some quantity squared over some angular region. So this is the cross-section. And this thing is what's called the amplitude. So basically, if you know what the Feynman amplitude is, or invariant amplitude is, you can calculate the cross-section. In fact, once you know this, you can also write down the decay rate. Decay rate is usually given as this, depending on the process. That can also be written as some function of this of the scattering. So in the whole course, we will not be worrying about calculating the cross-section. We worry about just calculating the amplitude. Because once you have this, it's a process of integration and then you can. So we just worry about this. Yes. That's right. And I also gave the examples of calculating the scattering amplitudes, for example. Different orders of perturbation theory. For example, for the QED, when it was done at tree level by Dirac, there was a discrepancy between the experimental value and the observed theoretical value, right? So the experimental value was the diamagnetic, this ratio, what was that? GE, right? So was approximately was 2 from the theory, but from the experiment it was only 2. So that's why people call this anomalous magnetic dipole moment, right? So later, when Schwinger did this one loop calculation, it was very accurate to second decimal place. Then the calculation was improved greatly. And as of 2015 or 2015, I think it's up to like 5 loops. So from 1928 to 2015, in nearly like 90 years or so, we could only go to 5 loops, right? So because doing these calculations are hard, and also why we should be worrying about these things, because whatever the new physics, it could be supersymmetry or extra dimensions or anything new. It doesn't have to be only these 2 things. Why we say this? Because these are popular, right? Everybody knows about these things, right? This doesn't have to be the case. Any new physics will have a small effect. If it's big effect, it could have been already detected even at Tevatron in Fermilab or at LHC by now. So for that, we have to eliminate all the background processes, mostly QCD processes. These are hadron colliders, so it's mostly quark-gluon interactions, this kind of thing. So I wrote down how at the tree level, when the number of gluons grows from, let's say, 4 to 10, the number of tree-level diagrams, only tree-level diagrams, was something like 10 million. So 10 million. So that means if we have a computer program which can calculate just the tree-level diagram, 1 second per diagram, so there are 10 million diagrams. So how much time will it take? So 1 second per diagram means that, let's say we have like 60 times 60 times 24 times, let's say 365. What's that number going to be? How big is it? Just do somebody. So it's going to be definitely about some 10 million, right? Take your iPhone 10s and do this. So I think we had something like 10 million for the.
Milhões?
30 milhões, 32, tudo. Let's say 30 millions. Okay, so this is 30 million seconds. So the diagrams for the 10 was 10 million, right? 10 million diagrams. So it takes like 4 months just to do the tree-level diagram. But that's not sufficient, right? So you have to do the 1 loop and 2 loop and everything. So now people call LHC as like a precision. They've entered the precision era in collider technology. That means they're calculating at least next to next 3D order. So this would involve, this is tree level, this 1 loop, this at least 2 loop and more, right? So that means it becomes just impossible. It's impossible, right? So that's why we have to find new techniques for finding the scattering amplitudes. That's our was our motivation. And also some of the, and I showed you this kind of things can become simpler in supersymmetric theories. So that's the reason why we are interested in supersymmetric theories. What's the reason? It makes our calculations easy, right? So whether it exists or not is a completely different question. Once we learn something from here, we can, from using supersymmetric theories, we can go back to our regular physics. So, so somebody asked a question. I think you asked a question. So how about doing the supersymmetric QED calculations and then do the thing, right? I did not find any, I did not search for this anymore. But I think that's a good question, so somebody can do that. Why I showed only gluons is because the colliders are hadron colliders. So the experiments were interested only in quarks and gluons. So that's why I showed that. Otherwise, it could be anything. The new collider, which is going to be bigger than LHC, may be built in China. And that usually what they do is when they build the collider, it will be electron-positron collider. And then they, after 10, 15 years, they will upgrade this to proton-proton colliders. That's been the tradition. Same thing with the LHC. What was the collider before the LHC? Large Hadron Collider. Before that was Large Electron-Positron Collider. Right? So this is the thing. So when they build the thing, it won't be in another 10 years. So that will be electron-positron collider. Maybe for those things, we need to calculate the electrodynamic processes rather than gluons and quarks, right? So that's it. It's like a supply-demand problem. So what experimental was? Theoretical physicists will calculate those things. Okay, so that's all we did last time, right? And I wrote down some processes in electrodynamics, some popular ones, including what were those, like Moeller process, Compton, Dirac, Bay creation, and these kind of things. So today we will calculate those things. And I thought like I can do like complete calculation maybe in 1 hour we can do these things. But later I realized no, they're like even the simplest thing will take like a lot of time. So I will try to do as much as possible. Maybe I will skip a few steps. But I will try to write down this as a lecture notes, include all the steps for all these processes if possible. Okay, so, and also I showed there were like 5 or 6 different methods for calculating the scattering amplitudes, right? So the first one was Feynman's in 1948, and then was Parke and Taylor. They found a new way. That was only for gluons. And then there was something like Chinese magic, right? And then unitarity methods. So all these methods can be used for any of the standard model processes. Later was Witten's program, right? So that's called the on-shell method, right? And then amplitude. That was only like 4 or 5 years. So I was interested in doing only the last 2 methods. But what is the point, right? So then let's first do this as much as possible, and then we'll go to that. So there is no hurry. So there is no hurry. And I want this to be quite informal. The idea is to learn something rather than just the names, right? So that's easy. Okay. So any questions so far? Any questions? What do you need? Okay, so what does this Feynman diagram method, right? So let's take some simple process. So A, B, C, B goes to C, X. So here, okay, so this is how the time is running. Although this is how the time is running, these diagrams are not space-time diagrams. So these are not space-time diagrams. Meaning what? These are not space-time diagrams. Look here, like this looks like both of them are happening at the same time, right? So this is not a space-time diagram. It's just a diagrammatic representation. This could happen before. Okay, but by the way, this is, if you write this process, this looks like this. So let's say a particle A comes, emits something, and continues. Right? So this This is space-time. So this is space-time. So particle A comes and emits some particle X and then continues. And now this particle is absorbed by particle B, and it changes its momentum and energy, and it becomes. So this is happening before this. This is happening. But it could as well be the other way. Meaning, it could be something like B comes first and emits this. So A takes that. What's happening here? B comes first, emits X, so it loses some energy and momentum. It goes to a different state. It's a D. And then the other particle A absorbs this X and then goes to this. Right? So then this is. So here there is a time order. So this is happening first. Here this is happening first. Whereas in this diagram, there is no time information. There is some time. It just says particle A comes. A and B come, and then something happens, they become C and D. Right? So there is no time order there. These are space-time diagrams. These are like Minkowski diagrams, space-time diagrams. This is not. So this is one of the most important things you have to learn about Feynman diagrams. They are not space-time diagrams. Right? Okay. First thing you have to learn about is Feynman diagram. So the second thing is, this is like a big calculation. This is like an equation in the form of a picture. Right? You know, people say like a picture is worth 1,000 words. If you have a picture, it's worth 1,000 words because it says so many things. But an equation is worth 1,000 pictures because you can write so many pictures. But here this picture is worth so many equations in this case. So okay, so it's sure. So what are the features of the Feynman diagram? Let's just do the anatomy of the Feynman diagrams, right? So like, if you studied like biology, they will take a frog and cut the frog, and then you do some anatomy, right? Like this. Let's. So this has something like external legs. These are the external legs. Right? So these are external legs. The first thing is yes. Let's say external lines. External lines. So for the incoming ones, we know what is the energy and momentum because we are sending them, and we can detect what is for the outgoing lines. So these external lines have they have P mu, right? So they can have spin. They can have polarization, helicity, and they can have many properties. They will have. So this state is defined by all these things. So external lines, and then is internal line. So this is an internal line. We don't see this in reality. All we see is AB going in and CD coming out. So we kind of reconstruct what happens here using our theories. So that's why Nima Arkanian of Princeton, he says scattering amplitudes tell the story of space-time. So for him, this is the story of space-time. That means they should say something about gravity and everything, like quantum gravity. Because all we know is what goes in and what comes out. And all we do is we reconstruct all the space-time drama that happens in this thing. So usually, how do final diagrams, they're like this. Three legs. So we don't know what happens. So using theory, we reconstruct what happens there, right? So that's why they tell something about the space-time itself. So that's why it's important to know about these things. Okay. So the internal lines involve propagators. These are the propagators. And we can derive the expression for the propagators using the Lagrangian of a given theory. So, in fact, I'll did this for QCD, for gluon propagator, in the axial gauge. Right? So, when you derive this, an expression for the propagator, it will be in certain gauge, right? So, and you need a Lagrangian for that. And then the other thing is vortex. So, vertices. These are the vertices. And that's where the interaction happens. So that's where the interaction happens. Again, this comes from the interaction part of the Lagrangian. So these things we know because we send whatever the prepared state of particles, right? So these things we know from our theories. So these things we know from Lagrangian. And there is so what do you do? Basically, what is the purpose of quantum field theory? Is to just derive these things. So starting from the Lagrangian, pick the interaction term and then use those things to find the propagators. This is the whole point of doing quantum field theory. So what do particle physicists do? Take these for interaction, these things, and then use this method to calculate the cross section, and experimental use to just measure it. So it's like three-part thing, right? So we have it theory. From the theory, you calculate the Feynman rules. Use them to calculate the cross section. That's phenomenologists. And then you go to experimentalists. So if you want to, like a food chain, right? So food chain is this is how it is. Theory to phenomenology, people just call field, like phenomenology. Phenomenology, okay. To experiment. So it's good to have some knowledge of these two things when you are doing this, so that you can constantly think about, oh, how can I verify my theory with experiment? That's the Feynman style of doing things, right? So always, whenever he does something, okay, so how can we verify this in experiment? And then what kind of experiment probably? He's not an experimentalist, he's not. So, but every time you have a theory, you should think about what can we do using the experiment, right? So, and how can we verify that using the experiment? That's phenomenology. So, in this thing, what I originally planned was not to derive these propagators or Lagrangians, but just take the Feynman rules and then calculate the amplitudes. So basically, this was my kind of bridge between theory and experiment. Just calculate the scattering amplitudes. Right? So this is vortex, and at each vortex there will be conservation loss. So we measure the incoming energy momentum. We know the outgoing energy and momentum. So we can tell what is the energy and momentum of this exchange particle using just the conservation of energy and momentum. Right? And this happens only at the tree level. If there is a loop, like here, this is the loop, we don't know. So you have to sum over all the possibilities. And that's where the integrations and infinities arise. Okay? So that's the different part. And also there are many conservations happening. For example, the electric charge should be conserved. Wattage should be conserved. So angular momentum should be conserved. Speeds and everything. So once you have this has a lot more information. So this is all about Feynman. We got the idea, right? So once we have a theory, that means we have a Lagrangian. Using the Lagrangian, we can calculate Feynman rules. Means all these things. And we can use that to calculate the amplitude, and from the amplitude we can calculate the cross section. So this is the full story of all of high energy physics. This is what we did. All of high energy physics. This is it. Okay. So any questions so far? Any questions? Today I want to calculate one of the scattering amplitudes for at least one or two processes, right? So, and before we get there, just for you to like relax and just be comfortable, I found some exercises here. I forgot to like print many copies of these things or like use the projector. So there you go. So I'll be drawing these things on the board without wasting much time. You tell me. So let's make it more interactive, right? So the question is, which is the correct Feynman diagram for pair annihilation and pair production? Right? So basically, what's that? I'm going to draw 4 diagrams. It's like a multiple choice question. Is it NA? So, is NA multiple choice? I don't know. Is it?
Yeah.
Yeah. So you are like, okay, we thought we are over. No, like because I found these things like a multiple choice. So this is. Just for the fun of it, right? So that you'll become more comfortable with these things. In all the cases, time is only this. So we have 4 diagrams. The question is, this has pair annihilation, means like electron, positron come together, they disappear and they make the photon, and then photon creates electron positron. Right? This is the pair annihilation and pair creation. So which of this diagram is representing the pair annihilation and pair creation, this process? C. Okay. So definitely there is no penalty for like guessing wrong. Maybe you should still get chocolate. I hope I have chocolate today. Even if the guess is wrong, okay? So don't have to worry about that. So C is the answer, right? So this is electron positron. Yes. Looks like this is the case. Okay. So here maybe I left out one crucial detail. we have particles and antiparticles, right? So how do we represent them in the Feynman diagram? What's the difference? When you look at this, can you tell? When the baby is born, you can tell whether the baby is boy or girl, right? So there's a method. Apparently this is not so simple. I had a friend, she had a turtle. She told that she discovered that the turtle is female after 10 years. So she took to the pet doctor, and he said, "Oh, you have a female for this? No, this turtle is a male for 10 years." So it's not that obvious that you think, right? So okay. So now when you look at the Feynman diagram, like looking at it, can you tell whether something is a particle or an antiparticle? And we know from Dirac. You all belong to Dirac-Istan. Right? So we know from Dirac that every fermion there's an antifermion. Right? So how do you know from the diagram whether it's a fermion or an antifermion? So one interpretation, this was discovered by Stuckelberg and Feynman separately, is the particles move in the direction of time, whereas antiparticles move in the opposite direction of time, as though they are moving backwards in time. They're time travelers, right? So we can go backwards if they're an antiparticle. It's backward in time. This is something like Feynman, Stuckelberg interpretation of antiparticles or something like this. So some people who don't like, who are jealous of Feynman, they call this as Feynman-Stuckelberg diagrams. And that person is Murray Gell-Mann. He's dead now, so this is, so what's the moral of the story? If the arrow is pointing in the opposite direction of time, that means it's an antiparticle, right? So now, do you want to change your answer, or do you want to do you know this? Who wants to be a millionaire kind of exam? So probably for you, India means like Slumdog Millionaire movie. So now I give you another chance. So why this is not the answer? Because the time is going this way, right? So both electron and positron are in the same direction as time. That can't be true, right? So that's why this is not the answer. Okay, so let's eliminate that. You can guess wrong, just randomly say any letter, that's fine. He's very brave. D? D? Okay. D. So let's see. Electron is in the direction of time, positron is in the opposite direction of time. Electron is in the direction of time, positron is in the opposite direction of time. Okay, it looks like that. This seems to be correct, right? But before that, we'll see why others are not correct. So this is not correct for the same reason. Right? But here it's correct. But this is wrong. So this diagram is not. What about here? This is correct, whereas here it's not correct. So this is the only correct answer. So that's one. I have a few of these, right? So just to Feynman diagram shows a beta plus decay. So this is so the previous, this is purely electrodynamics, quantum electrodynamics, and this is not. question is, which Fermat diagram shows the beta plus decay? Beta plus decay. What is beta plus? What is a beta decay? Before that, right? So, beta decay. In the case of there is some radioactive element X with some atomic number and some mass number, right? This becomes, this emits a beta particle. If it's beta minus, it's something like having one less proton, but this stays the same. So and usually some neutrino and some energy. So let's understand. So there is some radioactive element. So you all know about alpha, beta, gamma decay, right? So there is a radioactive element. It's unstable, so it emits a beta particle. Beta particle reduces the atomic number by 1. So this becomes a new element. So this is X became Y, completely on its own. So it's something like you bring a dog and suddenly it becomes cat and spits out some, let's say, a rat. So this kind of things happen at the atomic level. And there is this neutrino. Okay. By the way, if somebody writes down, okay, so this is at the face of it, right? Let's go a little deeper. Instead of at the nuclei level, let's go at the nucleon level, right? So at the level of protons and neutrons. What do you think is happening at the level of protons and neutrons? What is this Z? So that's correct, number of protons, right? So again, like when you are walking and then suddenly you find some element lying on the on the street. So you take this up and then can you tell what element is that? How do we know something is oxygen or something is hydrogen? We look into the nucleus. If there is one proton, oh, this is hydrogen, right? So as if we can see those things. But anyway, so here this is the number of protons. So what happened to the new element? The number of protons is reduced, right? So a proton has become, but the number of nucleons has stayed the same. So that means what? The number of protons plus neutrons is staying the same, but one proton is reduced. That means a proton has become a neutron. Boom. A proton has become a neutron, isn't it? And emitted this beta particle, beta minus. So is this correct? No, this is actually wrong here, right? Yes, it's already wrong here. It should be. So, what's the total number of protons before the reaction happened? Z. What's the total number of protons after the reaction? This plus that, right? So that makes it Z minus 2. So that's wrong. So this should be Z plus 1. Right? So this is how you can look at the equation and then what did we do? Here the charge conservation. The charge should be conserved. Should be Z plus 1. So that means it's not the proton which has become neutron. It's the other way. A neutron has become a proton. Right? A neutron has become a proton. And there is a beta particle. What is a beta particle? It's just an electron, right? So if somebody gives you a beta particle from the radioactive decay and an electron, you cannot look at them and then see, oh, this is from here, this is from here. You cannot make any difference. This is an electron. Now the question is this reaction correct? Is this complete? So charge-wise, what's the charge before? Electric charge is 0. This is +1. This is -1. Exactly. The charge is conserved. So, okay. But is there anything else wrong with this? See, everywhere there are some neutrinos, right? Why do we need neutrinos? We don't need, they are there, but so it's not just the conservation of charge. There are so many other conservation laws. Yeah? Very good. So the mass should be conserved, like energy, mass, energy. The momentum should be conserved. Other thing is other quantum numbers. What are the other quantum numbers you know, other than like spin and charge and stuff like this? Lepton number. Right? So what is the lepton number of a proton, of a neutron? 0. Right? So how do you know what's the lepton number? You ask the question whether it's a lepton or not. Is neutron a lepton? No. Right? So what are the only leptons we have? Electron, muon, tauon, and the corresponding neutrinos, right? These are the only leptons. So the lepton number of this is 0. The lepton number of the proton is 0. What's the lepton number of an electron? 1. So the question is electron a lepton? Yes. That means it's +1. It's 1. Okay. So what was the lepton number before this reaction happened? 0. Now, after the reaction, it's +1. So lepton number is not conserved. So that means this is not correct. There is something missing. This is our first neutrino was proposed. So what is that? Neutrino, right? There should be neutrino. If it's neutrino, is neutrino a lepton? Yes. So that makes this makes it +2, even worse. So this has to be a beautiful. It should be an anti-neutrino, right? So that the lepton number of that is -1. So now the lepton number is conserved. Right? So this is why this kind of conservation laws are so powerful. Just by looking at this, if you had done this, let's say, more than 100 years ago, you would be very famous for predicting a new particle. Right? So, Fermi, Pauli, these people are playing with this. That's how they predicted there should be a neutrino or some particle with this kind of nature in order to conserve the lepton number. So this is the reaction. So neutron. So we went from nuclear reaction. This is nuclear physics, right? So this is at the nucleus level to baryon levels, to the level of this. But now, if you look inside the neutron, what do we have inside the neutron? That's correct. so these are leptons, right? What are neutrons made of? Neutrons and protons made of. If you cut the neutron and proton, what do you get? Quarks. So what are the types of quarks we make? So there's up, down, then strange, and let's say write down this one. Top, bottom, and then chop. And this some people used to call them truth and beauty, but now it's just top and bottom. This was discovered only in the 90s. I don't know when, probably like maybe 93, 94. That's all. Yeah. So these are all the quarks, right? What is the charge on the up quark? Are any of these quarks? It's plus 2/3, and this is minus 1/3. So now you have the recipe. You know how to make. So you have to make a neutron using up and down quarks or any of these. Also, another open problem in particle physics is they're exactly the same, meaning they have the same charge and everything, but the masses are higher. Same thing was with the electron, muon, and tau. Right? So we don't know why there should be muon and tau, other than just being heavier than electron. So there is no good reason. So this is the 3 generations problem. And why do we have 3 generations? Why not 1? We don't know. Most of the stuff is made of up and down electron and electron neutron. Right? So not strange and bad. If you make something out of these things, it will just decay to something else. Right? So these are. So now, what is the recipe for neutron? How do you make a neutron out of these things? 1 up and 2 down, right? So yes, beautiful. So this could be neutrino. This neutron can be written as up, down, down, right? That goes towards the proton. Up, down. So plus and minus. So since one up and down have stayed the same, we can just take it up and down. So when we say it's beta decay, what is happening? A down quark is becoming an up quark, producing the beta minus of this thing. So these are the layers of reality, right? So you go from here to here like this. So isn't that beautiful? We can do all these things. Yes, so this is the case. This conserves everything, all the charge. Does this reaction conserve electric charge? What is the charge on the it's negative? 1/3. Up is positive 2/3 minus 1 plus 0. Yes, right. So this matches. It's minus 1. What about the lepton number? 0, 0, 1 minus 1. Yes. Yes.
I think every quantum number is associated with symmetry. Is that right?
That's correct. Yes.
So, which symmetry is the atomic number associated with?
Atomic number?
The
lepton number. Okay. So this association of symmetry, that's a very good question. Of the symmetry and the quantum number is for the continuous symmetries. These are
okay.
But this may not be the best answer, right? So these are discrete numbers, right? So these are discrete symmetries. So what is the symmetry associated with the lepton number? For example, okay, so these are like CPT, right? Charge conjugation, parity, and time reversal. These are discrete symmetries too, but they are related to together related to larger variables. So this was proved only recently, meaning like in the last 20-30 years or so. CPT invariance implies Lorentz invariance. So charge conjugation. So, but the lepton number, what is the symmetry associated with the lepton number? Now, so why should the charge be conserved? Charge conservation comes from UN symmetry. So, and lepton number is what is the that's a good question, right? You only ask questions that I can't answer. So you deserve a charge. I will give you. So the question is, so last time the question I could not answer was, is there any process that begins only at the one loop level, not at the tree level, right? I did not know the answer. Apparently it's the bright field, the photon happens only at the loop level. but I'll have to dig deeper, read and then confirm that. And now the question was, what is the symmetry associated with the conservation of lepton numbers? Okay. I don't know. Right. So whereas this charge, parity, and time conjugation, these are approximate symmetries, so they can be violated. So that means they may not be associated with something deeper in nature, but charge, together they should not be violated. If you have something where CPT is, but CP violation is okay, but not CPT together, that means the Lorentz invariance is broken. That's one of the ways how people who are interested in going beyond Lorentz invariance Lorentz violation, that's how they look for in the particle reactions. Right? So, but now to summarize the question, what is the symmetry associated with the lepton number? We'll think about it. I don't know the answer. That's a very good question. It's a very good question. Okay. So, yes, charge is conserved, lepton number is conserved.
Satish?
Yes.
What would happen if we violated the CPT symmetry?
You are violating the Lorentz invariance. If you violate the Lorentz invariance, what would happen? So CPT is Lorentz invariance. That's the theorem which proves this. What's the big deal about Lorentz invariance violation? For example, is this room, is the Lorentz invariance valid in this room? Right? The Lorentz invariance says it should not matter if there's a translation in space, right? So, and rotations and this kind of things. So obviously, if I go from here, it's not going to be the same. Oh, but if I did an experiment here and then do the same experiment here, that won't change because of the translation. Or if I rotate the instruments this direction, yes. So in that sense, yes, there is Lorentz invariance here. What is the big deal if we violate the Lorentz invariance?
It means that
Yes.
I think if an interaction happens in a specific spot in the space-time, and if this interaction happens in another specific point of space-time, and if you don't have, and if you don't keep the Lorentz invariance, so that should be difference.
One thing is Lorentz invariance, Lorentz violation doesn't mean causality violation. So just because there is no Lorentz invariance doesn't mean you can go back and kill your grandfather. why would anybody want to do that? Okay, so just saying. Okay, so that doesn't happen. For example, Newtonian physics, there is no Lorentz invariance, but there is causality, right? So if you have the Lorentz invariance, meaning you have the time listing, so this can affect only the things here, or be affected by only things here. So if something happens, it's not going to affect this. So that's what happens in the Lorentz invariance. But in the Newtonian theory, it's just like this. Anything here can affect anything there. So this has something to do with, and it can be here, it can be influenced by anything. So not just this kind of opens, this thing becomes like this whole thing. So this is all the future, this is all the past. That's how Newton's theory is, right? And also, Schrödinger equation is not Lorentz invariant. So it's not relativistic. So just because something is not Lorentz invariant or bias invariant is not necessarily bad. But there are some advantages of violating the Lorentz invariance. You can make quantum gravity work, this kind of things. It makes things simpler, just like supersymmetry. So there are like two ways to go beyond. One is break the Lorentz invariance, add supersymmetry, like two different ways of introduce new symmetry or break the. Otherwise, there are very tight constraints on the Lorentz violation. So, for example, if you do any like Planck scale physics, if there's a Lorentz violation, it can propagate to like real physics, low energy physics, and bring out a very huge change. So when you change the variables of the high energy, they have very high influence on the low energy. So in the case of fields, this is very correct. But some matter sector, like gravitation sector, like electron, all the matter, almost there is no chance you can violate the Lorentz invariance. Let's say it's an experimental fact. Whether you like it or not, it's the fact of nature, fact of life. But gravitation, there are not many experimental evidences whether gravity can violate Lorentz invariance or not. So that's why you can create theories with gravity, Lorentz violating theories. But matter-wise, there is not much room for doing this. That's a good question. So you will have many effects. For example, this can have superluminal speeds. So that means it can generate something called Cherenkov radiation. And if you have superluminal things and they are not generating Cherenkov radiation, that means that's not happening. Okay? So why should we respect CPT not violate that means Lorentz invariance? It's so far it's been experimentally proved. There is not a single result which violates Lorentz invariance at high energies. Yeah, that's a very good question. Yes, this relates to these things, right? Charge to lepton number violation. And also baryon number should not be violated. So for example, what's the number of baryons before? 1. Number of baryons later? 4. So this is 1. So right. So this matches. The baryon number also. For example, these things you can kind of violate in the case of black hole physics. So let's say you are outside the. You can just throw a proton into the black hole, and now the black hole. So earlier you had. Let's say this happens and this beta particle goes into the black hole. You are violating the lepton number and baryon numbers. So that's why these are not exact symmetry situation. But there should be a better answer than this. I'm not very happy with this answer, but this is an answer. not a very good one, but this is. Okay, so yes, this is what I want to show, like in many layers. Okay, so tell me which of these. Oh, by the way, this is not beta minus, right? So this reaction is beta plus. So in that case, what happens if it's beta plus? Let's just re-engineer everything, right? So you can see from here. So instead of down turning into up, the up turns into down, right? So you don't have to go back here and then go back. So up becomes down. Let's just verify here. So you know this is positive, right? So beta plus is positive. We can just verify. Let's see if the charge is conserved here. What's the charge on this one? Plus 2, right? So that comes in and then these two go out. So this should be equal to what? Plus 2 thirds. It's going right. So should be equal to minus 1 third plus 1 because this is double plus, right? By the way, what is the interaction? Okay, this is actually what is the interaction involved in this? In this experiment, this is a photon, right? What is the interaction here? Electrodynamics, right? Because it's photon. What about this one? what is the exchange particle? What's the boson gluon? Is it the gluon or W plus W minus or what? It's W minus, right? So that means it's a weak interaction. All the decays are mediated by weak bosons. So only weak interaction can turn something into something else. So it made down into up, up into down. So you can change. Whereas here, it's not the case. They stay the same. It doesn't change the particle. So weak interaction can change things into something else. Okay. So here this is conserved, right? Because this is true. We also know this convention time. Let's eliminate some of the possibilities. One of them is definitely wrong.
There is a positron or is a beta plus? Should be a beta plus or a positron?
They are the same.
They are the same?
Exactly.
Ah.
So very good question, very good question. So beta minus and electron, beta plus and a positron are the same. And this is coming from electrodynamics. This is from nuclear physics, right? It's the same thing. It's just different name. People call them by different names. Beta particle, which is beta minus, is same as an electron. Beta plus is same as a positron. So yes.
Why these diagrams can't represent a strong interaction, for example?
Why can't they? Good question, very good. So here, what's the exchange particle? What's the boson? Are all W's, right? So that means it's a weak. If it's mediated by a gluon, then it would have been the case. But the question is, why is it not a gluon? Let's say we don't know what that is, right? So can we say it's a gluon? First of all, it cannot be neutral because of this tendency. See, the up goes here down. So this has plus 2/3. It cannot be neutral. So that means it cannot be Z0, or it cannot be gluon, it cannot be photon. It has to be W plus or W minus because there's for two reasons. One is one thing is becoming something else. That means it's a weak interaction. Any decay means weak interaction. And also, it has to be a charged particle. So the only charged bosons we know, the vector bosons we know, are W plus and W minus. So it cannot be gluons, it cannot be photon, it cannot be only Z0. Let's use this knowledge of like here, right? So if we have a antiparticle, it should be going backward in time. Yes, yes. Yes.
You can rule out A and D for the same reason. Previous one.
A and B. So they're going backwards in time, right? Oh, you mean
No.
so
A and B.
Let's see. Let's first use this knowledge of eliminating the antiparticle should be traveling backwards in time. That's easy to eliminate, right? In one of them is the case. Which one is that? So this is backwards. Electron is going backwards. Oh, okay. You're saying. See here, this is a positron, but it's going forward in time.
Yeah.
So this
That's the strong.
right? That's what. And here we have a neutrino, but it's going backwards in time.
Okay. Yeah.
So that's not either. Here we have anti-neutrino. Oh, look at that. Going forward in time. No, that's not the case. Looks like this is the only option. And another reason, this is anti-particle. This is also anti-particle. That means the lepton number is not conserved. This cannot be the case. Same thing here. This cannot be the case. That's what it is. So looks like everything is working out fine for this one, right? This is the answer. Yes.
Is the down part going back in time?
Oh. So that means in this diagram, this is not how the time is running. Oh, okay. So we will have to be a calculation. That's correct. It cannot be the case. So the time is going upward. So very good question. So time is going upward. So this is all fine. This is all fine. This is all fine. Okay. But here, this is back. This is correct. This is not correct, right? That's not correct. Whoa, that's really good. That's good observation. So this cannot be the this because this is going backwards. This is not. What about here? This cannot be right because it's going forward. What about here? This is correct. This is also backward in time. So the left-hand number should be considered. Here, it's going forward, this is correct. So this is the correct answer. Right? Why C is not the thing? Because although the labels are correct, the charge, the left-hand number is not considered. Both positive. Yeah, no, that's correct. This is -1, this is -2 because it's anti-neutral. So that's right. Any objections? That's very good observation. Very good. Yes, go ahead. Yes, no problem. Say the question.
Why letter C is not correct?
Why letter C is not correct? Okay. So time is going this way.
Okay.
This seems to be right. Anti-particle going backwards in time. Everything is fine. And charge seems to be all conserved, but lepton number is not conserved. So what's the lepton number before something happened? 0. There are no leptons. Yes, these are quarks. So there is no lepton number. So what's the lepton number after? This is it's an anti-particle, so it's -1. This is an anti-neutrino, so it's -1. So we have -2 lepton number before we have 0.
Is anti-neutrino going back to time, so is a neutrino.
No, so it's a neutrino going backward in time. That's why we call this anti-neutrino. Right. So this is an electron going backwards in time. That's why we call this positron. So this is like symbolic way, let's say English way, like letters. Using letter we are saying this is anti, and using symbol we are saying anti. So it's not. Any objections? Guess what? Like I have something like some 15 examples of like this. I thought like we can do just in 1 minute and then move on. But there are more. Let's not spend more time on this thing. But this is good. Right? So, let's do the actual calculation. So this is how you can play with. Maybe I will make copies of this. I did not want to scare you like giving homework. So I'll give you this. By the way, like, where do you think I took these questions from? Like, at what level of education? This is from like a graduate course or like a. This is from high school. The last chapter in high school physics involves Feynman diagrams for whatever reason, I don't know, right? They're not studying surface tension, viscosity, but they're studying Feynman diagrams. These are questions from high school physics.